Okay, the recording is on. Yeah, so today is our third lecture on this quantum computing course. And then let's briefly recap what we've done last time, and today we will dedicate our time to basically practice and exercise of what we learned so far, because I guess this is like important to uh, to master these ideas before we get to the actual course. Right? So last time we said that we basically continue into discussion these Hermitian matrices, and the Hermitian matrix is the matrix that uh, coincides with with itself after Hermitian conjugation operation, which is transposition and complex conjugation. Right, and two main properties of these Hermitian matrices are that their eigenvalues are real, and this is important for quantum because in quantum mechanics all real quantities are real valued, right? So in quantum mechanics all real quantities are represented by Hermitian matrices and Hermitian operators. We will discuss that in what follows. And the second property is that eigenvectors of Hermitian matrix represents a basis, meaning that we can use the eigenvectors of a Hermitian matrix to basically to span our vector space, to represent any vector state or basically any vector in this vector space. So then we say that basically any operator can be represented by its matrix, and vice versa. Any matrix can be represented by uh, in the operator's notations. Then we derive these basically formulas how we basically transit between matrix and operators notations, and then we consider this example of Hermitian matrix. What else? Yes, then we discussed other operations with matrices. For the first one was this matrix product. Basically, any two matrices like A and B can be you can take this matrix product. What else? Then properties of matrix product. Then inverse matrix, right? This we discussed how basically how we can find the reversed matrix of any matrix. I mean, not any, for a matrix with non-zero determinant. Otherwise, if determinant of a matrix is zero, then the matrix is so-called singular, right? It doesn't have a inverse matrix. What else? And then we start discussing these unitary matrices, unitary matrix or unitary operator. We say that unitary matrix is the matrix that so this is the formula, right? This is the main basically definition. So in order to check whether the matrix is unitary, you first take the Hermitian conjugation and then check if the result coincides with the inverse of the same matrix, or by multiplying this equation by matrix U, right? On the right side, you will get what? You will get U Hermitian conjugation times U equals to I. I is the identity matrix, meaning that the product of the Hermitian matrix with the product of a if a product of a matrix with its Hermitian conjugated matrix gives you identity matrix, then this matrix is unitary. And the unitary matrix is a very important kind of matrix that describes an operation in the linear space, in linear vector space, that keeps the inner product of two vectors unchanged, right? You apply this operation on any vector, it rotates the vector but doesn't change the length of the vector, and also doesn't change the inner product, the dot product of any two vectors. One example of unitary matrix in our Euclidean space is this rotation matrix. That basically does what? It for in a given space, it for a given basis, like here x, y, it rotates the basis by some angle phi, right? Of course, the vector doesn't change after this transformation, and this matrix allows you to calculate the components of your vector in the new basis. As you can see, there are infinite number of different bases, basically, that differ basically only by the angle of rotation in this space, because this phi can be like any number, and all these bases are completely equivalent. You can use any of those. And then we introduce this bracket notation, or also known as Dirac notation. So in this notation, we represent a vector, for example, vector x. Let me maybe choose another color. Yeah, any vector x, right? It will be a column of numbers, basically projections. So these x1, x2, etc., xn are projections of a vector in a given basis, right? So the vector itself is an object. The object doesn't change when you rotate the basis, when you change the basis, the object. But when you select a basis, then you can project this vector onto the basis vectors, and those projections are x sub 1, x sub 2, and all the way up to x sub n, where n is the dimensionality of our vector space, right? And the so-called dual vector, which is also known as bra vector, in this notation it is written this way. It is just transformed. It can be represented, it's connected to its ket vector by transposition and complex conjugation. So it's in contrast to ket vector, the bra vector is a string of numbers like this. And this notation allows you to write the inner product as the usual complex as the usual matrix product in this form, right? And also the outer product. So basically, inner product is the, this is this form, bracket, right? The outer product is the kind of reverse. So you put first cat and then bra. And following the standard matrix notation for the matrix product, this product gives you the matrix. So the inner product gives you the number. In general case, it is a complex number. Outer product gives you the result of this product is the matrix, or this matrix can be thought of as an operator, this operator, right? And then we discuss the action of this operator on a vector, and after acting of this operator on the vector, you obtain actually another another vector in the same vector space. So now let's practice maybe what we discussed so far. And here I prepared a number of problems. And so let's start with the first one. Let me turn off the camera. Okay. So the first problem. So by the way, do you all see my screen, the tablet, nicely?
Yes, we can see it.
Okay. So the first problem. So for two given vectors in bracket notations, vector A with components 2, minus 7, I is the imaginary unit, right? 1. And another vector B with components 1 plus 3I, 4, 8. So two vectors. And also we have a scalar A that equals to 6 plus 5I. Okay, so the problem is find what? The product of scalar and vector A, the product of scalar and the sum of vectors A plus vector B, then inner product of A and B, inner product of B and A, and check if these inner products are equal or not. So let me maybe change another color for solution. Okay. So the first one, A times, let's denote this A. So A times vector A. Vector A. Right. So our scalar A is equal to 6 plus 5I, and our vector is 2 minus 7I, 1. So this is vector. Okay, so how we take the product of scalar and vector? We simply multiply each entity of the matrix or of a vector by this scalar, meaning that the first component will be 2 times 6 plus 5I, which is 12 plus 10I, right? Then minus 7I times 6 plus 5I, and the third one is 1 times 6 plus 5I, which is 6 plus 5I. Okay, so now the first component is okay, 12 plus 10I, then expand the brackets, minus 7i times 6 equals to minus 42i, right? And then plus minus and I times I, which is equal to I squared, equals to minus 1, right? So it is equal to 35, and the sign is plus, because minus and minus gives you plus. So plus 35, and here x 6 plus 5i. Okay, and solution, of course, I mean the imaginary part of the complex numbers should stand on the second the second part. So the first one is this 12 plus 10i, then 35 minus 42i, and 6 plus 5i. Okay, so this is the first the first one. The second one, B. It is, so the problem is to find A times vector A plus B, right? So A times A, vector A, we just find this is the result. So we need to find this, we need to find the product of A times vector B. So it is 6 plus 5i times vector B, 1 plus 3i, 4, 8. 1 plus 3i, 4, 8, exactly. Okay, so it is equal to 6 plus 5i times 1 plus 3i, then basically 4 times 6 plus 5i, and 8 times 6 plus 5i. Okay, I do it step by step. So here we expand the brackets, multiply each term in the brackets, right? So it is 6 plus 18i plus 5i and minus 15. The second one is 24 plus 20i, and the third one 48 plus 40i. Okay, so now here minus 15 plus 6 minus minus 9, right? And then plus 23i, 24 plus 24, 20i, and 48 plus 40i. So this is the result, and now for this here. Okay. So we have what? We have 12 plus 10i, 35 minus 35 minus 42i, 6 plus 5i, and plus the second vector, which is minus 9 plus 23i, 24 plus 20i, 48 plus 40i. Right. So how we find the sum of two vectors? We basically sum the components of the vectors, right? and the real parts, some with real parts, imaginary parts with some with imaginary parts. So here 12 minus 9 equal 3, then plus 33i. This is the first component. The second one is 35 plus 24 equals 59 minus 22i. And the last one 54 plus 45i. So this is the this is the result for the part B. So next, the third one, the inner product. So the part C, inner product of A and B. So first of all, where is the vector A? Vector A is this one, vector A. And now we need to first to write this bra vector. So now this vector A in the cat representation, we have to rewrite this in a bra representation, meaning that we have to take the transpose of this vector, basically write this in as a string of numbers, and complex conjugation. So this second component minus 7i will change to 7i. Right, so we write this for the A. It will be 2, then 7i, and 1. And now the vector B is 1 plus 3i for 8. 1 plus 3i for 8. Okay, so this is inner product. I just remind you how we find this. We take the basically the row by column, right? So in this case, we have only one row in the first vector, the matrix, and one column in the second one. So basically, this is the sum of the products of the corresponding components. So it will be 2 times 1 plus I. Let me write this right away. So it will be 2 plus 6i. Then the second one, 7i times 4, which is 28i. And plus 1 times 8, which is 8. Okay, so
Dr. Alex, I have a question.
Yes.
The A matrix has a the second element has minus 7i. Is it changed there?
No, the matrix A matrix A is this one, 2 minus 7i 1, but in the cat notation. In the bra notation, you transpose this, so the column becomes the string, and you complex conjugate it. So minus 7i becomes 7i.
Yes. Okay,
B vector in the cat representation, in this formula, you see this A,
yes.
bra A times B cat. So B goes as a cat, and initially it was this one, right? So
Yes.
I don't change this B. Okay, yeah, so don't hesitate to ask any questions, right? Because this is like very important to to practice this. So 2 plus 8, 10, and 28 plus 6, 34i. So this is the result. So now let's find the opposite, right? This B, A. It was A by B, now it's B by A. Basically the same inner product, but the vectors changed their representation from bra to cat. Right. So now this vector b is the row. So this is my vector b here, right? So I transpose this and complex conjugate. Complex conjugate, meaning that this first one, the first component will be 1 minus 3i. So it was 1 plus 3i. I complex conjugate, so minus I turns to minus I. So that's why minus 3i. This is the first component, second component is 4, and the third is 8. And vector A in the cat representation is 2 minus 7i and 1. Again, the the same procedure. What we get? We get 2, right? Then minus 6i, then minus 28i, then plus 8 equals 2, 10, and now minus 34i. So we see that we conclude that the product AB doesn't equal to the product BA. Doesn't equal to, and actually, in fact, and let's try this in red. The product AB is equal to BA complex conjugated, and this is like a general result. So let's write it general result. So basically, the inner product of two vectors, if you exchange the vectors, the result is complex conjugated. Okay, do you have any questions regarding to this first problem? Very simple one. The only thing, maybe the only new to the actual, the usual vectors is just this representation in bra and cat.
No question, Professor.
Okay, so let's go to the second problem, and where it is. Find the norm of each vector. Find the norm. Norm is the synonym to the length, right? But length, I mean, usually when we talk about length, some vector has a length, we mean the vector in our Euclidean space, geometric space. The norm is a more general thing, and we will see that a norm or a length can be I mean, you can find this norm or the length of a more sophisticated object, so it's like it's called function vectors or function space. We will discuss that also. All right, so find the norm of each vector normalize the vectors. Normalization of a vector means change basically the vector in a way to make the vector norm to be equal basically 1, or length of the vector will be 1. So the vectors are a vector 2 minus 7i 1, and the vector b is 1 plus 3i 4 8. Right, basically the previous vectors from the previous problem. So the norm, right? How we how we find the norm? So the norm denoted by two vertical lines. This is the norm of the vector A. Right, this is just the notation. And how we find the norm? The norm of a vector is equal to the square root of the inner product of the vector by itself. Basically, A. Okay. So to find this inner product of vector A by itself, we need to rewrite this ket vector in a bra vector. So it will be 2, then plus 7i, right, because of the complex conjugation, and then 1. Sometimes I write these commas in the string, sometimes I don't. Just like if these elements separate like enough, then you can simply not write the commas there. Otherwise, you better divide the elements by comma to avoid any confusion. So and the ket, the vector A in ket representation, which is 2 minus 7i and 1. Okay, so the same procedure. 2 by 2 is 4, then plus 7 by 7, 48, 49, and minus, and I squared also gives you minus, so it will be plus 49, and plus 1 by 1 equals 1. 49, 50, 54. Right. So 54. Okay. So
I have
the
a question,
norm.
Professor.
Yes.
Yeah, but I was thinking that the norm of A should have been like a ket vector of A times a ket vector of A. Why it become a bra and a ket?
Yes. So this is. Let's return to our discussion when we introduce this chi and bra, ket and bra.
Okay.
So basically, the point is that any vector, like any single vector, can be written in the bra and ket representation. It will be the same vector, exactly the same vector, but written in two forms: in form of a ket and in form of a bra. And why we do so? We do so because we are dealing with complex vectors, and when we calculate the inner products, dot products of two vectors, we have to take one of them transposed, and since they are complex, we have to complex conjugate it. That's why we introduce this bra notation.
Okay.
But of course, the vector itself doesn't change when we transpose this and complex conjugate it. It is just the way how we write the same vector.
Okay. Okay.
So yeah, before when we calculate the scalar product of two vectors, we would write something like a vector dot a vector.
Yes.
In our case. So as you can see, if you want to write these vectors in this column form, then this second, because of the matrix product notations or rules, right? The second matrix or a second vector must be a column, then the first one must be a row. That's why we have to.
Okay. Yeah, now I understand.
Yeah. Thank you very much for the questions. It's very, very important to go back sometimes and discuss why we do so. Okay, so the norm is the square root from a times a, right? So in our case, this is square root from 54. 54 is the what? Is the 6 times 9, right? Oh, sorry, it's square root of 2. Right, so and square root of 2 from 9 is 3, so it is 3 square root from 6. Okay, so for the second vector, b times b, it is here. So let's write this in a bra notation. So it will be 1 minus 3i, then oops, okay, 4 and 8. Right, and the second one is 1 plus 3i 4 8. The same way. The same way. So maybe about this. So 1 minus 3i times 1 plus 3i. This is the complex number times complex conjugated number, right? Which is the modulus of this number squared, which is the real part squared plus imaginary part squared. So 1 squared here is 1, 3 squared is 9, so 9 plus 1 is 10. The 10, then plus 4 by 4 16, plus 8 by 8 64, which is equal to 90. Right. So the norm of vector b is equal to square root from 90. 90 is 10 times 9. So I can write this 3 square root from 10. Okay, so now the problem say or ask us to normalize the vectors. How we do normalize the vectors? Let's denote the vector a by n, normalized vector. So basically we need to divide the vector by its norm, right? If you take a vector of length, let's say 10, you find the length, divide the vector by its length, then you get the vector of the length 1. So, and we name this normalized vector. So our norm of a vector a was 3 square root of 6, so we divided. So write 1 over 3 square root of 6. And then the vector itself, which was 2 minus 7i and 1. Okay, so this is my first normalized vector. If you calculate the length of this vector, you will get 1, because we just normalized it. And for the second one, b normalized, we will have what? 1 over 3 square root of 10. And then vector itself, which is 1 plus 3i 4 8. Okay. Why it's important? You probably know that in quantum mechanics we deal with probabilities and probabilities amplitudes, and probability always has the maximum value of 1. right? The one, like 100% certainty. The probability amplitude is 1. That's why in quantum mechanics we have to know how to normalize the vectors. Okay, so let's go to the problem number 3. Check whether the following vectors are orthogonal and normalized. So the problem are the following vectors orthogonal, question mark, normalized, question mark, and the vectors are psi vector 1 over square root of 2 and 1 over square root of 2. And another vector phi, which is 1 over square root of 2 and minus 1 over square root of 2. Okay. So orthogonal, what does it mean? Orthogonal means that their inner product is 0. Basically, this is the same like terminology as we used to when a vector A is orthogonal to the vector B. That means the product of vector, the scalar product of vector A times vector B is 0. Or in other words, the projection of vector A on the vector B is 0, right? Or projection of vector B to the vector A is 0. This is the same in this space. Right, so orthogonal. Let's check. So how to do so? We take the inner product of vector phi and vector psi. Phi vector, so the components are real valued. In order to get the bra, I just transpose the vector phi square root of 2. And vector psi is 1 over square root of 2, 1 over square root of 2. As far as I remember, something like this you've got in your homework assignment. So component by component. 1 square root of 2 times 1 square root of 2 gives you 1 over 2. Right. 1 over square root of 2 times 1 over square root of 2, 1 over 2, and then minus 1 because of this minus here, right? Minus 1 square root of 2 times 1 over square root of 2 gives you minus 1 over 2, which is 0. So these vectors are orthogonal. Vectors are orthogonal. And how we check if they are normalized? We basically go and find their norm. So the norm of vector phi is equal to what? 1 over square root of 2 minus 1 over square root of 2. First, the bra and the ket is 1 over square root of 2 minus 1 over square root of 2. Okay, components by components. The row by column. So 1 over square root of 2, 1 over square root of 2 is 1 over 2. then plus minus 1 over square root of 2 minus 1 over square root of 2 is plus 1 over square root of 2. Half by half gives you 1. This is 1. And hence the norm of vector phi is 1. So the vector is normalized. And what about the psi vector? The psi vector basically the same, but the sign, right? 1 over square root of 2, 1 over square root of 2, and the column 1 over square root of 2, 1 over square root of 2, which is 1 half plus 1 half equals 1. So the norm of psi is equal to 1. The vectors are normalized. Their length is 1. That's it. So this is the solution to the third problem. Do you have any questions? If no, let's go to the next one, the fourth one. Check whether the following vectors linearly independent. Linearly independent. So the first one is A 2 0 0. The B vector is 0 minus 1 0. And the C vector is 0 0 minus 4. Right. From here you can immediately say that they are orthogonal, and since they are orthogonal, they are linearly independent. But we know this definition for the vectors to be linearly independent, which says that for any constants, let's denote them by a1, a2, a3. For any constants like this, if this identity satisfied, it's not identity, it's if this expression holds, a1 a vector plus a2 b vector plus a3 c vector is not equal to 0, then the vectors are linearly independent. So this is the definition. And the meaning is that you can use these linearly independent vectors to basically span any vector in your vector space, or represent any vector in your vectoral space. So let's go and find this for our vectors. So we write a1 and then vector a, which is 2 0 0, then plus a2 vector b is 0 minus 1 0, and then plus constant a3 0 0 minus 4. So the product of the constant a1, for example, by the vector, we take the product of each component of the vector by this constant. So we get 2a1 0 0, plus, this is the first vector, second one 0 minus a2 0, plus a3 0 0 minus 4a3, right? And this is the sum of three vectors. How we find it? Basically the sum of each component of all corresponding components. of the first one is 2a1 plus 0 plus 0. The second one is 0 minus a2 plus 0. And the third is 0, 0 minus 4a3. Right. So from here we conclude that for any a1, a2, and 3 that's not equal to 0, right? Because this expression here must be valid for any constant a1, a2, and 3. So for any a1, a2, and 3, but zeros, this is not equal to 0. Hence, the vectors a, b, and c are linearly independent. Linearly independent. They linearly independent. That means that they are basically orthogonal, and we can use them as a basis. Let's check that. Let's check that they are orthogonal. For example, for this vector a and b. Right. For the vector a, we have 0, 2, 0, 0, and the vector b is 0, minus 1, 0. So from here you see that all the products of the components equals 0, so it equals to 0. As well as the all other products like a by c is equal to 0 and b time vector c is equal to 0. So they all are orthogonal. and so they are linearly independent, they are orthogonal, and if you normalize them, their lengths, for example, if you divide this first vector by 2, the second one by by minus 1, and the fourth by minus 4, you will get the basis, right? The complete set of orthogonal and orthonormal vectors, and you can use them as a basis to expand any in your space. I'm saying this so many times in order to make you used to this terminology. So the next one, the 5, right? The 5. Normalize the vector psi, which is equal to 3i times vector phi1 plus 2 times phi2 and minus 4i vector 3 phi3. And these vectors phi1, phi2, phi3, let's denote them by phi. Phi sub I, they are orthonormal. Orthonormal vectors. What it means? It means that any product like phi, let's say 1 and phi2 equals to 0 because they are orthogonal, and any product like phi1 equals to 1 because they are normalized, normal. Okay. And what we need to normalize this vector psi here. So as you can see, and this is what we discussed several times already, that you can take a vector, any vector in our in some space, in this space we have chosen an orthonormal basis of vectors phi1, phi2, phi3. They are orthonormal, so we can use them as a basis. And now I expand my vector psi over these vectors with their projections, right? This this projection to the vector phi1 is 3i, the projection to the second vector is 2, and the projection to the third one is minus 4i. Let me maybe actually draw this, how it looks like. I mean, how you can imagine this. So we have a space, we introduce this vector psi1, like another vector c2 and another vector c3, right? So this is the on the orthonormal basis in our space. And then I have some sort of a state vector, some vector psi, and I'm finding the projections of this vector psi onto these these vectors of the basis. And for example, this projection at the first vector, this phi1, is equal to what? It's equal to 3i. For this, I mean, for this in this particular case, the projection on the second axis is 2, and the projection on the third one is minus 4i. So as you can see, these projections are complex valued. So this is definitely not the kind of space that we used to, right? Because projection is complex valued. In our real space and Euclidean space, these projections are always real valued. But in quantum mechanics, we have to like go beyond to these complex spaces. All right. So our task is to normalize this vector. And first of all, we know that this vector is written in the ket notations, and we have to rewrite this in the bra notation. So this psi in the bra notation. Basically, I transpose and complex conjugate, so all these ket vectors will become the bra vectors, and the constants they will complex conjugate, right? So this 3i, sorry, will be minus 3i, and then this bra vector phi1 plus 2, it doesn't change, and then the bra vector phi2, and then minus actually plus 4i phi3. Okay, and now I find the inner product of psi by itself, right? And and here I have to multiply each component. For example, this this component bra psi phi1 by phi1, then by phi2, and by phi3. But all of these products, phi1 by phi2, is equal to 0, because the vectors are orthogonal. And phi1 by phi3 also. So because of the orthogonality of these vectors, all the products of different vectors is equal to 0, and the products of the vectors itself is equal to 1. So for example, for the first one, I will have 3i phi1 times minus 3i phi1. Phi1 by phi1 gives you 1. So I'll get minus 3i times plus 3i, which is 9. 9. Then plus the same way 4. And finally 16. So the result is 29. So the norm of psi vector is square root from 29, and the psi vector normalized is equal to 1 over square root of 29, then 3i phi1 plus 2 phi2 minus 4i phi3. That's it. We just normalized the vector. Do you have any questions?
No question.
Very good. Okay, so let's go to the next one. So the problem is as follows. Represent vector.
Hello.
Yes?
Sorry, I don't
Excuse me? Do you have any?
know if my volume's in here. I was just wondering if you could elaborate a little. It's not working. I can.
Yeah, I can hear you. What's your question?
My question was. So there's. So the last is circled, and then there's two a little bit more on. Okay.
By the way, do you hear me well? On
Yeah,
my
I hear
side,
you well. Yeah, it's her. Yeah.
Yeah, can hear you very well.
So did you get the question? What was the question?
She's typing it right now, I think.
Okay. Very good. Can you write out 5, 5? Yeah, sorry, maybe I skipped this part. Let me write this in more detail, right? So basically this part here. So we write psi. So the bra psi is equal to minus 3i phi 1, then plus 2 phi 2 plus 4i phi 3 vector times, I can see it on the screen, it's just me. Do you see my screen and how I'm writing this?
Yes, Professor, you can see your screen.
Yeah, so
I mean, I can see your screen.
So this probably on your side something. Not the new notes. That's weird. Let me disconnect my my VPN, FIU VPN. So maybe that's because of this, and it probably will lag a little on my side, but just on a very just a little. So it's disconnecting. connected back. So do you hear me now? Do you hear me now?
Yes, Professor, for me, yes.
Okay. All right. So so now it's probably will be better. Sometimes I get this problem because of this FIU VPN. So in the second the second part, right? It is 3i phi1 plus 2 phi2 minus 4i 3 phi3 equals 2. So I take the product of each component by each component. Like for example, this one by this one. I get what? I get minus 3i times 3i. It is 9 because I times I gives me minus 1, and I have another minus here, so it's 9. And then what? Then phi1 bra and phi1 ket. Right. Then plus, and the second one. So I take this the first term in the first in the first bracket and multiply it by the second term here, right? So it will be minus 3 times 2, and here I get this phi bra times phi 1 times phi 2. But this term is equal to 0 because because the vectors are orthogonal. So their scalar product, their inner product is equal to 0. And the same way, all other products of different vectors, like phi1, phi3, phi3, phi2, etc., all of them basically equal to 0 and don't contribute to this, to the final result. So let me say this is 0, right? On the other hand, all product of vectors by itself is equal to 1 because the vector is normalized. So like for example, this phi1 by phi1 is equal to 1. Phi2 by phi2 also is equal to 1. Phi3 by phi3 is also equals to 1. And only the prefactors, these prefactors by the products of the vectors survive, right? So from, I mean, let me write this plus blah blah blah, which is equal to 9 from the first product. Then phi2 by phi2 equals 1, but 2 by 2 equals 4. So I write plus 4. And then finally phi by 3, 1, but 4i times minus 4i is equal to 16. So it's plus 16, right? So it's 20, 29. Okay. So this is basically how we write the products. So the next problem is not a problem actually. It's a sort of like a useful new useful information, but we're gonna derive this. So the problem is represent a vector. Present a vector psi in the basis U. Like this, right? So this is our basis. find the coefficients. Basically, coefficients. Basically projections, right? Projection coefficients in the bra and cat in the bra and cat representations. So the basis of vectors ui, right? Let's denote as like basis cat. And dual to this basis cat will be a basis of bra vectors. So like physically or geometrically, this is the same vectors, but the way we reproduce them can be bra representation and cat representation. So this is dual basis, also known as basis bra. And since this is a basis, that means that all the vectors are orthonormal, which means the product like vector I times vector j, right? And I and j any number from this set, and the result will be equal to what? The delta Kronecker's delta ij. And in this case, this is the same as the unitary matrix or identity matrix, which is 1 0 0 blah 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 0 1 0 blah 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 0 0 1 blah blah blah, etc. Right. So the diagonal matrix with units at the main diagonal and all other components equal to 0. Delta ij. So this is basically means that the vectors are orthogonal. If I and j are different, then the vectors are orthogonal, and the result of their product is 0. But if the vectors are like identical, like when I equals to I, then these vectors are identical and their product gives you 1 because the vectors are normalized. So the fact that I have this basis, I can now represent any vector, this vector psi, in my basis the following, right? So the projection of this vector on the basis vector u1 plus the projection of this vector on the basis u2 plus the projection on the vector u3 plus etc. all the way up to cn un. Very good. So now I can rewrite this in a short format using this summation sign, right? So the sign n cn vector un, right? So now in order to find the coefficients, these projection coefficients, I multiply this by the bra vector m. So m can be any vector from from this from this basis. So I multiply from the left both sides. So I write um here vector and then this vector psi right on this side. On this side. So this is the result of the product. And and the second one, right? The second right side. So it will be um times the sum n, and here cn un vector. So the product of a vector by a sum, right, a series is equal to the product of the vector by every term in the series. So it's equal to the sum, and Cn is a constant, so I can take it out, Cn, and then we have this inner product, un, right? So now let's look at this expression here, and note that this is equal to actually to the delta identity matrix or delta matrix because the vectors are orthonormal. So this is equal to delta mn now. So it's equal to let me write it here, sum over n cn delta mn. So now all components of for a given m delta mn all equal to 0 when n not equal to m, right? But when n equals m, this delta equals to 1, and only one term in this series survives, which is cm, So now comparing this and this, I conclude that cm is equal to un psi, as it's supposed to be, because this is just a projection of a vector psi on a vector um. And m here can be, I mean, it's any number from the basis, so it can be cm un psi. Right. So this is just projection of a state vector on one of the basis vectors. Okay, but the problem also asks us to find the same in the bra notation. So what about the bra notation? So in bra notation, our psi vector will be another series Cn with the bra unit vectors un, right? Other basis vectors. So now we multiply the same on the right by ket vector m, and follow the same procedure. From this we will get cm, but psi times um. So as you can see, the difference only in the order of the product. Basically, the projection in the ket and projection in the bra notation differ by complex conjugation, right? Because the inner product of two vectors differ by the complex conjugation. If you sweep the psi and u, you have basically you get the same but complex conjugated. Okay, so basically this is this solves the problem. But now let's let's use this fact and rewrite this. So let's return to this to this formula. Representation of psi vector as a C n u n, right? So now let's use this fact and plug in this formula to this one. So what we get? We get sum of n u n psi times u n. Okay. So this is vector, this is number. I can of course exchange the order. I multiply them. I can rewrite this in this form. Un vector, and then this un vector bra and psi vector, sum over n. And now we here we notice this form, like here we have this psi vector, right, and something that acts on this psi vector here. So this is some sort of an operator. But here we have on the left hand side we have psi, and on the right hand side we have psi. So this is basically an operator that doesn't change anything. What is this? And this is basically identity operator, right? So we conclude that this this operator here, which is sum over n un is identity operator. Pretty important fact. That we will use this for several for many times in the course. So basically it says that if our vectors u are orthonormal and represent a basis, we can basically write this form here, take the outer product of two vectors un, take the sum over all n in our space, and the result will be just unitary matrix or identity. Sorry, not unitary, and identity matrix. I repeat that I is equal to something like this, etc. Identity matrix. The matrix that basically doesn't change anything. Basically, if you multiply this matrix I times vector psi, in result you get vector psi. Doesn't change anything. All right, so now let's go ahead and practice a little the operators. So let's write operators here. Operators, and just like as a reminder, an operator we usually denote them by this small hat on top, right? So this is the typical sign of an operator, and we can multiply this operator by our unit vectors u, let's say n, or let's m here, and vector un here. So we multiply this operator by unit vectors from right and left, right? And this is simply written without these products, because this is actually not a product. This is action of the operator on a vector. So I write this in a more correct form: un t vector t operator um, and this is the same as t and m, right? Basically just the elements of my operator, or elements of a matrix that corresponds to the operator. Okay, and now let's practice this a little. So this seventh, right? This, yeah, the seventh problem is in orthonormal basis. In orthonormal basis, with unit vectors, orthonormal vectors un, u1, u2, and u3. Operator A. Operator A acts as follows. So basically I have operator, then my operator, for example, acts on the first vector from this basis, and the result, for example, is equal to 2 times u1. So basically this operator, when it acts on a first vector from this basis, the result is just multiplication of this vector by 2. So what this operator does, it simply extends or makes the vector longer by twice, right? 2 times longer. When the same operator acts on the second vector from this basis, the result is, for example, 3u1 minus I u3. So now we see that this operator is doing something more interesting, because in contrast to the first vector, the second vector, it transforms this to the combination of other vectors, which is something more interesting. And the third operation of this operator A on a third vector u3 is, and it's equal to minus u2. Okay, so this is the set of rules of the action of the operator A on a orthogonal basis u1, u2, u3. This is again, this is just example. This is not general, right? So this is just example what a particular operator A can do, these operations. So now we need to write this operator A in matrix form. So operator A, and we know that there is a matrix that corresponds to this operator, A11 and Y2, A13. This is a three-dimensional space, so the operator will be like matrix 3 by 3. So it's A21, A22, A23, A31, A32, A33. So this is the matrix V after. Okay, so let's take the first rule from here, right? And first element we want to find is this A11. So we take the first rule and multiply by U1 on the left. So multiply this first rule by U1 on the left. It gives us the following, right? So this is U1 times operator A, U1 is equal to 2 is a constant, and here this U1 and times U1 from here. This U1 here and here. Okay, U1 times U1 is equal to what? Is equal to 1, because the vectors are orthonormal. So the the result is 2. So we conclude that, let's write this step by step. So the component is the component A11, which is the same as the U1 operator A U1, this construction, in this particular case is equal to 2. So we can go ahead and fill up this first element of our matrix here, 2. So next we need the component A12. I mean, as well as all other components. So I suggest to take the first rule and multiply this rule on the left by the remaining 2 vectors. So the product of vector u2 by this a u1, right, is equal to what? It will be 2 times u2 times 1. u2 u1 is equal to 0, right? The vectors are orthogonal. So this is 0. And on the other hand, this is the component A21. A21. Next, the component A31. I multiply this first rule by U3 on the left. So it will be U3 A U1 is equal to 2 U3 U1 is equal to what? 0, because the U3 and U1 are orthogonal. Next, go to the second rule, this one, this rule, and and do basically the same. So I write A12, which is A1 AU2. So I multiply this rule by U1 on the left, and I see that the first term is survived because it is U1 element. So 3 U1 by U1 gives me 1, and the second is minus I U1 by U3, which is 0. So this component is equal to 3. The second one, the A22, I multiply this rule by U2 on the left side. I notice that here and here I have no u2 vector, right? So the product of u2 by u1 and by u3 gives me 0. So I conclude that the component a22 is equal to 0. And next, a32. The same way, I multiply by u3. The first term is gone. The second one is equal to minus I. And now let's jump to the third rule here. And so for this rule, I will get the components with the second index free, right? So I can write 1, 3 first, multiply this by u1, and this give me 0. Then a 2, 3, u2 by u2 is 1 and minus 1. And finally u3, 3, multiplying this rule by u3 on the left, the product u3 u2 is 0, so I get 0. Okay, and now let's sum up everything. So a12 is equal to 3. a13 a1 what is it? a13 is equal to 0. a21 is equal to 0. a22 is equal to 0. a23 is equal to minus 1. a31 is equal to 0. a32 is equal to minus I. a33 is equal to 0. So this is the matrix of this operator in the matrix representation. Let's check if this matrix is Hermitian. So Hermitian. So what is Hermitian? You remember that the matrix is Hermitian if it coincides with the Hermitian conjugated matrix. Like in this case, we should check that this matrix A is equal to the matrix A Hermitian conjugated, A dagger. And A dagger, I remind you, is the transpose and complex conjugation operation. You basically apply first transpose and then complex conjugate the elements, or vice versa. The order here doesn't matter. So let's write the transposed matrix A. Transposed. What I get? So I have this main diagonal, right? The main diagonal elements don't change, and I rotate all the elements by 180 degrees, or basically exchange the replace the rows by columns and vice versa. So what I get? I get the matrix, of course, with elements 2, 0, 0, then here 3, 0 minus I, 0 minus 1, 0. Right. And now I complex conjugate this matrix. And what I do, I just change the minus of this imaginary unit. So the result is 2, 0, 0, 3, 0, I, 0 minus 1, 0. Right. And this is definitely doesn't coincide with the matrix. So the matrix A are not Hermitian. Not Hermitian. But what about unitary? Is this matrix unitary? 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 So I remind you again that a unitary matrix is such a matrix that when you take the Hermitian conjugation, A dagger, it is equal to the inverse matrix, A minus 1, this inverse matrix. This is by definition. And from here, what we can do, we can simply check that the Hermitian matrix times the matrix itself gives me the identity matrix. Right. I again remind you how we get this. We get this from here. So if my A dagger equals to A minus 1 inverse matrix, then I can simply multiply the both from right or left side by the matrix itself, and I will get A dagger A, and here A inverse A. But by definition, this A inverse A is the identity matrix I, right? So I conclude that A dagger A is equal to identity matrix for the, I mean, only if A is unitary. Only if A is unitary. So let's check that our matrix, whether the matrix is unitary or not. So what we get, our matrix A is equal to 2, 3. So where is the A? A is here. 2, 3, 0, 0, 0, minus 1. 2, 3, 0, 0, 0, minus 1. And 0 minus I, 0. 0 minus I, 0. This is A itself. And now I take the product, matrix product by the Hermitian conjugated matrix, which is this guy here. So it is 2, 0, 0, then 3, 0, I, and then 0, minus 1, 0. Right. So again, this is A matrix and this is A dagger, Hermitian conjugated matrix. We take the product rows by columns, as usual, rows by columns. So 2 by 2 is equal 4. 2 by 2 is equal 4, plus 3 by 3 is equal 9, plus 0, 0 is 0, so 4 by 9 is equal 13, right? Then the second element, 2 by 0, 0, 3 by 0, 0, 0 by minus 1, 0. The next element, 2 by 0, no, 0, 3 by I, 3I, and 0 by 0, 0. Next, the second row, 0, 0, minus 1, 0, so it is 0. Next, minus 1 by minus 1 gives me 1. Then minus 1 times 0 is 0, so it's 0. And the third one, 0 to 0 minus I 3, so it is minus 3I. Here 0 0 0. Next 0, and the last one is minus I times I is 1. So this is 1. So this is definitely not equal to identity matrix, right? So the matrix I is not Hermitian. Is not Hermitian. This is the procedure of finding either the matrix unitary or Hermitian, etc. Of course, usually you don't do like by hand. Usually I use this MATLAB or Mathematica. Mathematica, for example, is very powerful in this case because, I mean, for this matrix calculations, because it allows symbol calculations. So basically you can put any letters there and still computes the I mean, everything basically gives you the result. Yes. So yeah, so basically this is the answer to the 7th problem. So let's go next and let's consider this interesting problem, number 8. So now let's represent operator A. This one 1 minus 2i 0. Is it Hermitian or not? So if you transpose, you will get plus here minus here, I mean of this of diagonals, and then complex conjugate, so it will be exactly equal to this A operator. So this operator is is Hermitian. So represent this operator, this Hermitian operator, in in the outer product notation. So this is quite important. This is quite important part here. So what does it mean to represent a operator in the outer product notation? So first of all, let's recall that operator in this matrix form is nothing but the matrix of these these constructions, right? U1, the operator A, U1, then the second element is U1, A operator U2, then here U2, A operator U1, and finally U2, A operator U2, right? So basically the elements 1, 1, 1, 2, 2, 1, 2, 2. This is by definition. So now let's go ahead and rewrite this operator here. This one, 1 minus 2i 0. I see that, for example, this 1 must be equal to this construction here, U1, A, U1. All right. So let's rewrite this in the following form. I guess this is like the best way to write this. Just write and see how it works. So I I take this first element, which is 1, and then multiply by outer product of vectors u1 by u1, then plus the second element, which is minus 2i by outer vectors, outer product of vectors u1 u2, right? Because this is the element 1 2, so I take multiplying of the product of u1 by u2, then plus this element 2i, and the vectors are u2 u1, because this is element 2 1, and finally plus 0 times u2 u2. Okay. And now let's just check that if I take the product of this, for example, by u1 u1 on left and right side, I will get exactly this element here, right? So I take my operator in this form, multiply by u1 on left and u1 on right. And I know that everything like u1, u2, u1, u3, right, all this is equal to 0. And u1, u1 is equal to 1. So let me multiply this. So I get u1, then this first term here, right, which is 1, then u1, u1, and this u1 on the right side, so this u1 here. Then plus minus 2i, u1, u1, u2, u1, plus, let me clean this up. Then the second one, 2i, and the vectors u1, u2, then u1, u1. And finally 0, u1, then u2, then u2, and then u1. That's it. So now I see that now I check what terms not equal to 0. So this one definitely equals to 0 because it multiplied by 0, but also it gets 2 times this product u1 u2 u2 u1, which both equal to 0. So this is definitely equal to 0. Next, this guy here u1 u1 equals to 1 because the vector is normal, but this guy here u1 u2 is equal to 0 because the vectors are orthogonal. Here the same, this u1 u1 equals to 1, but u2 u1 gives me 0. And finally here I have u1 u1, it is 1, and another u1 u1 equals another one. So finally I get only one coefficient survived, which is 1. exactly my element. And you can check that like for all others, like if you take, for example, u1 a u2, you will get this element 1 2 here, so it will be minus 2i. And the same way u2 a u1 will give you 2i, and u2 a u2 will be equal to 0 because this component of the matrix is equal to 0. So this means that sorry, that this representation of a of a of a of an operator, right? Of this operator is fair. This means that you can write an operator in the outward outward notation, outward product notation. So let's let's write this in a general case. So oops. So in general case, if you have a operator given you in a matrix form, for example, like this 2 by 2 operator, you can rewrite this operator in the outward product notation as the first element, then the product of the outward product of these two vectors u1, u1, then the second element 1, 2, the product u1, u2, plus the third one 2, 1, u2, u1, plus the fourth one u2, 2, u2 cross u2. Or I can write the same this way. The sum over n and over m, so basically the sum runs twice, of elements a, n, m, and out products u, n, u, m. This is the general formula. So now let's and this works for any matrix, any operator. So now, as an example, let's take this identity operator I, which doesn't do anything, as we discussed already, and write for this operator I. So we will get this sum n and m over n and m. The matrix elements of the identity operator is deltas n, m, right? And in a given basis, we have un, um, here and here. Okay, so since this deltas equal to 1 when n equal m, and otherwise they equal to 0, so only elements with the same indices survive, and they equal to 1. So this simplifies to the single sum over n, let's say, of this un, un. And this is exactly what we already saw, that we can represent identity matrix as in this way, as a sum of these operators un times un. It was somewhere here, right? So this formula today. Okay. Next, find the trace. But before that, let me tell you what the trace operation is. So the trace, let's choose another color, maybe, I don't know, like this. Trace trace of an operator. For example, operator A with components A11, A12, etc., A21, A22, etc., all the way up to AN1, AN2, etc. So we have this operator, right? The trace is denoted by, usually it's just TR trace. The trace of this operator A is equal to the sum over the diagonal elements. So these are diagonal elements here, and we basically just sum these diagonal elements over. So it is equal to n sum over n. So this is definition of trace. The same way we can, of course, the product, like the trace of product of two operators, operator A, operator B, and one property of this trace is that the trace doesn't depend of the product, like the product of operator A times operator B will be equal to the trace of operator B times operator A, so it doesn't affect the result. And maybe more important property is that trace doesn't depend on the basis, trace doesn't depend on basis. So what it means? It means that this operator, it gets these elements, right? We can represent the let's look at this formula here. So we can represent our operator in the matrix form, and when we do so, we take this product of these basis vectors with the operator. But the point is that these basis vectors, they are not unique. What we discussed in the beginning of today's lecture is that we can rotate this basis as we like, and so there is an infinite number of different bases. And when we rotate this basis, of course, the matrix elements also change accordingly. But the function that operator does, of course, doesn't change on the choice of an of the basis. And speaking about trace, the trace doesn't depend on the choice of the basis, and this is something important for the following. And now let's consider this problem 9. Find the trace of matrix A, which is 13, 0, 3i, I, 0, 6, 8, 4. This is the matrix, and the problem is to find the trace of this matrix, trace of A. And so this is very simple. Just I sum up all the main diagonal coefficients, which are 13 plus 5i plus 4, which is equal to 17 plus 5i. That's it. So this is the trace of this matrix. Very, very good. So do you have any questions?
No, Professor.
Very good. So let's well, let's discuss another one, and maybe or maybe yeah, another one, and there will be the next one, but that will be very very simple, and and both of these will be like useful for your homework. So in some bases, the problem 10 in some bases the the operator T is represented this way. So it will be phi1 plus 2 phi1 phi2 plus phi2 phi1, and that's it. No element phi2 by phi2, which means that the coefficient is equal to 0. 0, I can write this way, phi2 by phi2. So you see that this is the outer product representation of the operator T. So I can go ahead and transform this representation to the matrix form, right? So I have this 1 here, so it is 1, then 2 here, it will be 2, then 1 here, and 0 here. That's it. So this is my matrix representation of this operator T. So for this operator, find the eigenvectors, and eigenvalues. Eigenvectors, eigenvalues, very important concepts, right? You will see that eigenvalues of operators from quantum mechanics represent the basically the quantities that we, or values of physical quantity that we measure in experiment or obtain in our quantum computer simulations or something like that. So basically eigenvalues, for example, eigenvalues of, let's say this way, energy, right, in quantum mechanics corresponds to the so-called energy operator or Hamiltonian of a system. And then when you find the eigenvalues of the Hamiltonian operator, you will get like numbers or functions, and those are the energies that a system can basically obtain, and not other, like the other values of energy not allowed, only from this set of eigenvalues. So find eigenvectors and eigenvalues. The typical procedure is as follows, and we start from finding the eigenvalues. We discussed this briefly like last time probably. Let's recall how we do so. Let me change my color. So for my my matrix T 1 2 1 0, right, I write this determinant of this matrix T minus alpha, which is some constant, and this is the eigenvalues, right? It will give me the eigenvalues alpha times identity matrix, because here I have matrix, so like 2 by 2, and hence this part also must be a matrix 2 by 2. Okay. Oops. Okay, so it's equal to determinant of what? Matrix 1, 2, 1, 0. So this is the T matrix. And now I have to subtract this alpha times identity matrix. Identity matrix has elements 1 at the diagonal elements, right? So this guy here this second term won't change the off diagonal elements, but diagonal elements get this minus alpha here, and is it ended? Sorry, do you hear me?
Yes, Professor, we can.
Oh, okay. My screen just changed, and I thought maybe the meeting is ended. All right, so yeah, so minus alpha here as well. And now I have to find the determinant. Determinant here is the product of diagonal minus the product of off-diagonal elements. All right, so it will be 1 minus alpha times alpha minus 2 is equal to, yeah, and this is characteristic equation, right? And this matrix has non-zero solutions, right? If this characteristic expression is equal to 0, so this is the characteristic equation. Now I expand these brackets here, so I get alpha minus alpha squared minus 2 is equal to 0. Hence, alpha squared minus alpha plus 2 is equal to oops, something. Is it? Give me a second. Minus alpha.
Looks like there's a minus that is missing on the first term. Minus lambda on the equation.
Oh, yeah, sorry. Yes, exactly. I'm just looking what I missed here. So it's minus alpha here. Yeah, thank you. So here we have minus alpha, then plus alpha here. Okay, so now it makes sense. Alpha squared minus alpha and minus 2 equals to 0. Right, so discriminant is equal to b squared 1 minus minus 4ac, which is basically times 2 minus 2, right? So it is 9. So the square root from discriminant is equal to 3, and hence the alpha, the lambda lambda 1 is equal to 1 plus 3 over 2, which is 2, and lambda 2 is equal to 1 minus 3 over 2, which is minus 1. So alpha 1 equals 2 and alpha 2 equals minus 1. These are eigenvalues of the matrix T. Matrix T. So now I remind you the meaning of these eigenvalues and eigenvectors, right? So the equation for the eigenvectors and eigenvalues is this one. So my operator T times vector A is equal to lambda A. So basically, if this holds, right? If my the action of my operator on a vector is consists in multiplying this vector by this lambda. In general case, is not the case. In general case, it will be another like vector pointing in another direction. But if I manage to find a vector A so that the product of this vector A and matrix T consists in or results in the same vector but multiplied by lambda here, then this vector is equal to, this vector is eigenvector. And this alpha or lambda is eigenvalue. And we already found these eigenvalues of this matrix. It is two matrix or two eigenvalues. And now we just need to find the eigenvectors. Eigenvectors. So for that, let's choose the first one. For lambda 1 is equal to 2. We simply write this equation here. So the matrix is 1, 2, 1, 0. Then I should multiply this by components of the eigenvector, and I don't know this eigenvector yet, right? So let's denote it by a1, a2. So this is the components of my eigenvector, and it's equal to lambda, which is 2 times the same vector, a1, a2. Right. So now let's take this product here, which is equal to a1 plus 2a2, the first component. The second component is a1, and it's equal to 2a1, a2. So from here I conclude that a2, for example, equals to 2a1 equals to 2a2. a1 equals to 2a2. So the first eigenvector, let's denote it by vector 1. Let's say it is it gets the components 2a1, 2a2, a2. We don't know this a2 yet, but we can find this from the normalization. So from normalization, we take the product of a1 by a1. It's equal to 4a2 squared plus a2 squared, and we make it equal to 1 because we normalize the vector. So it's therefore 5a2 squared is equal to 1. Therefore a2 is equal to 1 over square root of 5. So we conclude that our first eigenvector is equal to 1 over square root of 5, and components 2 and 1. So this is the first vector. The first eigenvector. Again, for a given matrix, this one, written in some basis, presented here, all right, with these components, when I this matrix on any vector from my space, I get, in general case, I get another vector. But there are two vectors which are called eigenvectors that are being acted by the matrix T. Don't change basically the direction, but only get multiplied by eigenvalue. And yeah, now we searching for these eigenvectors now. So for the second one, for lambda 2, which is -1, right? -1, we write the same, basically a1 plus 2a2 over a1, it's equal to -1 a1 a2, right? From here we conclude that a2 is equal to minus a1. So our second vector is equal to a1 and minus a1, because a2 is equal to minus a1. So from the normalization, 2 squared is equal to 1, and hence the a2 is equal to 1 over square root of 2. So the second eigenvector is equal to 1 over square root of 2, and here 1 minus 1. Okay. So why it's so interesting? These eigenvectors. I just want to repeat this, like to explain everything, to make it very clear. So this matrix T is a matrix 2 by 2, and it's written in some basis phi1, phi2, according to this problem statement, right? And we have just found another two vectors, a1, a2, which are eigenvectors of this matrix, which eigenvectors. And now, if I represent my matrix in this new basis, because a1, a2, these eigenvectors, they represent another basis, and I can transform my matrix to this another basis. And when I transform this matrix to this eigenbasis, my matrix T will transform to a new one, which is diagonal. So instead of this one, 1, 2, 1, 0, I will get simply a matrix of eigenvalues, basically 2 and 0 here, and then 0 here, minus 1 here. So this is the same matrix, but transformed to another basis, to its eigenbasis. And this eigenbasis, the matrix becomes orthogonal. And this statement holds for like any operators, any matrices, including what I said about the Hamiltonian, of a space. When I describe something in quantum mechanics, I write the Hamiltonian of this system, and basically what I do then, I represent this Hamiltonian in a matrix form, and then do this eigenstate eigenvalues problem. I solve this problem, make the Hamiltonian diagonal, and these diagonal elements, they represent the energy states that I measure in experiment or obtain in quantum simulations, etc. So this is basically how it works. And general like solution in a quantum theory, right, is basically to find or construct the right Hamiltonian and then diagonalize the Hamiltonian. And in some sense, you can say that the quantum computer, we will discuss that in much more detail soon, but you can simply say that a quantum computer is a system that takes as an input the Hamiltonian basically in a, not only Hamiltonian, some state matrix in some state, some state, and in the output you get the diagonalized elements. This is how it works. As an example, let's consider very important matrix for the following. So as a problem like star, let's describe this. Let's find the eigenvalues of this matrix sigma z, which is Pauli, one of 3 Pauli matrices. Pauli matrix 1 0 0 minus 1. Pauli matrix. And do we need any calculations here? We don't, because this matrix is already diagonal. So this sigma z is diagonal, which means the diagonal elements are already eigenvalues. So the eigenvalues of this matrix 1 and minus 1. And no need to diagonalize this matrix. And in fact, this matrix has very important eigenvectors, and we will discuss this next time. And these eigenvectors basically is the representation of a qubit in quantum physics. So, but let's prove that this diagonal matrix, I mean, its elements are already eigenvalues. To do so, we write this equation for the eigenvalues and eigenvectors. Basically, this matrix sigma z, then vector u1, u2, right? Then it's supposed to be equal to lambda u1, u2. So we need to solve this. So this sigma z is equal to 1, 0, 0 minus 1, the matrix. Then u1, u2 here is equal to lambda u1, u2. Now take this product, right? And the first element will be simply u1, because 1 times u1 is u1, 0 times u2 is 0. So the first one u1, the second one is equal to minus u2, and simply equal to lambda u1 times u1 u2. So from here we conclude that lambda 1 is equal to what? Is equal to simply 1, and lambda 2 is equal to minus 1. That's it. So this is 1 minus 1, the diagonal elements of this sigma z. So the problem of finding the eigenvalues of any matrix consists in diagonalization of the matrix. Diagonalization of a matrix and eigenvalues the procedure of finding eigenvalues of a matrix, basically this is the same, like different way to say the same thing. And let's lastly discuss one thing that will be useful for you to do the your homework. So this was which one? Tens. So let's discuss another one, 11s. An 11 product. Find matrix X that satisfies the matrix equation. Matrix equation X plus A times B equals to 0. So here X, A, and B are matrices. And you, in your homework assignment, you have some specific matrices for this A and B, and this equation is different. But now I just wanna like show you important point here. So let's go ahead and expand the brackets. And from now on, for example, I cannot write something like bx plus ba. So this is completely wrong. When I deal with matrices, in a general case, the result of a product, for example, a matrix A by B, is not the same as B by A. So we say that matrices are, let's say, don't commute. In general, they don't commute. Meaning that the result of a product A by B is not equal to the result of the product B times A. So this is important point here. And actually for the following course, we even introduce this commutator. We denoted by this rectangle bracket, then A, comma B, and this is equal to operator or matrix A times operator or matrix B minus operator or matrix B times operator or matrix A. So this is commutator. This is commutator. If this commutator is equal to 0, the matrices commute. And in this sense, in this case, it doesn't matter which matrix goes first and which is second. But in general case and in your homework, they don't commute, and you should track the order of the matrices. For example, in this case, the right way to multiply this would be X times B, then plus A times B equals to 0. So now we go. So our goal, our problem is to express X, matrix X. So we transfer this A times B to the right side. We get XB equals to minus A times B. All right. And now we need to get this X, and usually what we do, we just divide both parts by B, right? And that's it. But this is completely wrong for the matrices, because a matrix, we cannot divide like matrix A by another matrix B. This is wrong. We cannot do that. for a matrix, we have to multiply our matrix by the inverse matrix. So let's multiply, in this case, let's multiply this both parts of this equation by inverse matrix B from the right side. So it will be x b b inverse equals to minus a b b inverse. So now we recall that it doesn't matter in what order we multiply the matrices, right? So we can multiply these two first, and this product of B and B inverse is the identity matrix. And here is also identity matrix. So, and this equal to X identity equals to minus A identity, and identity by any matrix equals to the matrix itself. So it will be A here minus A here. In your case, in the homework, it will be something different. So you should be very careful with that, because you will get some inverse matrix of a combination of matrices in there. So please be careful with that. And yeah, so this is basically it for today. If you got any questions about your homework, we can discuss next time. I also going to make another assignment based on what we done today. I will take a couple of these problems and just slightly change the problems, the numbers here and there, and then make this assignment. So you will get a chance to practice with everything what we discussed. So a good thing is that this is almost all the math that we need to proceed, and I mean proceed to the further. Next time we will start discussing the the basics of quantum mechanics. Just briefly, only those essential points that we need to, like, I mean, to master the quantum computations and quantum informatics, and and I also will give you several. I mean, we will discuss the qubits and like 3 different ways how we usually realize a qubit in a lab. It is a state qubit, a spin qubit, and a polarization qubit. So these 3 types of qubits, these are the basically the all qubits that we or people use now to build a quantum computer. Yes. So let me do this weekend. No, I mean usually I give you time, like 2 or 3 weeks. Let me stop recording and we can discuss.